Welcome back, campers. Morgan here. We're on page 11 of the thermochemistry outline for Honors Chem, and we're continuing our discussion of spontaneity. And we're going to talk about the driving force. Now, the driving force is which of the three factors cause a reaction to happen. Now that might be the enthalpy, the entropy, or the temperature. Okay? So, silly question, but it makes my point really well here. Do you have to do work to heat up a tea kettle? If you put that tea kettle full of water on the stove, do you have to do work to make the water hot? And the answer is yes. And what that means is absorbing heat requires work to be done. Okay? That's when delta H naught equals a positive number, or what we might call endothermic. Do you have to do work for a tea kettle to cool off? No. That's releasing heat. And that happens quite spontaneously. Okay, systems give off heat, of course, relative to the temperature that's, surrounding them. Okay, we assume we're talking at 25 degrees Celsius here. So that's when delta H naught equals a negative number, or is something that's exothermic. So I have to do work for something to absorb heat. I don't have to do work for it to lose it. Do you have to do work for your room to get cleaned up? The answer is yes. Absolutely, that requires work, okay? That is a decrease in entropy. Or that's when we're saying delta S naught equals a negative number. And that requires effort on somebody's part. Of course, you don't have to do work for your room to get messy. It just kind of happens. That is an increase in entropy. And that's when delta S naught equals a positive. So like we were saying with the example of the coins on the last page, increases in entropy tend to happen. That's the way nature points. Decreases in entropy, not so much. So what we're talking about is who's doing the work. Is it the system or is it the surroundings? And you are part of the surroundings. So if you have to do work, the reaction is not going to be spontaneous. Okay? Now, pretty much every year that I've ever taught chemistry, some kid has asked me, hey, if I mix these two chemicals, will they explode? What they really are asking is the reaction spontaneous? And this table is going to give us some clues about that. Now, what we just said was releasing heat and becoming disorganized do not require any work. So if the enthalpy is negative and the entropy is positive, your free energy is always going to be negative. Enthalpy is delta H, entropy is delta S, and the free energy is delta G. And when this is negative and this is positive, free energy is negative at all temperatures, every single time. Now, the opposite, delta H positive and delta S negative. Heat has to go in, it has to become more organized. That's not spontaneous. Both of those require work on my part, okay? So that is non-spontaneous at all temperatures. Now, we could also have positive, positive, we could have negative, negative. Now, in this case, it all depends upon the temperature. Delta G can be positive or negative. If the enthalpy is positive and the entropy is positive, it is spontaneous at high temperature. Because that absorbs heat, endothermic, right? So at a high temperature, there's a lot of heat for it to absorb. It becomes disorganized. At higher temperatures cause more disorganization among the particles. So that would leave this one, negative, negative, to be spontaneous at low temperatures. And since this is exothermic, a low temperature means it can release even more heat. Okay? So, the driving force. In this first example, both things drive the reaction, enthalpy and entropy. In the second example, neither drive the reaction. It's non-spontaneous. But in this third example, the entropy drives the reaction, dependent upon the temperature, because delta S is positive, and that does not require us to do work. We don't have to do work for it to get more disorganized. And when they're negative, negative, the enthalpy is the driving force. Driving force. Driving force. And that's what causes the chemical reaction to happen. Okay, on the next page, we'll look at some different examples of this. Thanks for tuning in. This is Morgan signing off.